Hello students, and welcome to another video. I'm your teacher, Mr. Flynn, and today we're going to be talking about the atomic emission spectra. Okay? And we're going to be using the Bohr model to describe how this mechanism works. Okay? There are many ways that we can view the atom, and one of those ways is the Bohr model. Okay? The Bohr model is a little bit primitive compared to what we have today, but it is good to use in this example because it can easily illustrate how this mechanism works. Okay? But please keep in mind, there are more complicated ways of looking at the atom that are more accurate, but this model works. Okay, so I want you to write down this definition. The atomic emission spectrum, okay, is the pattern formed when light emitted by an element is separated into different wavelengths it contains. All right, so if we look here, we have two light sources. We have an incandescent light bulb, and we have a hydrogen lamp. Okay, incandescent light will send a full spectrum of colors, right? You'll see red, orange, yellow, green, blue, and violet, etc. Okay, Roy G. Biv, okay? Yeah, if you've taken physics, this section will help you, okay? And it's being separated by a prism, okay? A prism is what breaks that light apart, because white light is the presence of all the colors, right? So your eyeball, okay, can actually see this light, all right, and you're interpreting white as the presence of all the colors combined. But when we break apart white light, it will actually separate into different colors. All right. Now hydrogen, okay, when we do a hydrogen lamp, if we take hydrogen, we can actually excite the electrons and they move energy levels. I will talk about it in a minute. All right. And as they move levels, they actually release light. All right. And it actually only releases very specific wavelengths of light. All right, and that's actually one of the ways that we can identify atoms. All right, now there's more. We actually use a lot of these type of gas lights because what's happening is we have a gas of hydrogen, and what we're doing is we're putting electricity through it, and there's actually causing this cascading event to occur. And what's happening is these electrons are moving energy levels, and I'll talk about what they are in a minute. And as they move, they release light. Right, that energy that's being put into those electrons being moved releases light. And the lights in our classroom are doing the exact same thing. Who's ever been on the road? You've ever been driving down the road and it's at night and you see those orangish kind of colored lights, right? And you were driving and you kind of just see one every so often as they light the road. Those lights are actually made out of sodium. They're sodium lights, this Na right here. Okay, they have a sodium gas, and they're exciting them, and it actually creates that kind of orangish yellow color that we see at night. All right, and we use this in our classrooms too. We have mercury bulbs. Okay, mercury is Hg. All right, it's in a gaseous form. We're exciting those electrons, and they're releasing light. Now, the difference between the sun and atoms is that the sun releases a full spectrum, just like this incandescent bulb, while atoms only release very specific wavelengths of light. And we'll talk more about it as we go, okay? There's an introduction. Now, we have here hydrogen, helium, sodium, copper, and strontium, and an unknown. And each of these atoms, if you give them energy, will release wavelengths of light that are very specific, okay? And if we look here, hydrogen, it's a rather simple element with only mostly one electron, so it's only going to have a couple lines, while more of these complex elements with more electrons that are moving around in that cloud are actually releasing more bands of light. Okay, and please keep in mind, this is only the visible spectrum. Okay, we have other spectrums to include as well. All right, we have the ultraviolet, which is higher energy waves, and then we have lower energy waves, which are infrared. Okay, so the electromagnetic spectrum is basically a classification system for the wavelength of waves. Okay, and we're only seeing the visible section of that. Okay, could there be lines outside of this? Yes, there could be. If you had a detector that could detect them, you could pick up those waves, all right, of those different magnitudes. But our eyes are only fitted to see a very small section of this spectrum. Okay, another good example is if you ever used an infrared camera. Right? Infrared is picking up infrared radiation, which is a bit longer wavelengths below this certain spectrum. Okay? If you're a little confused, all right, I will probably find you some videos on this, and we'll have discussions in class. Okay? But if you're watching this video, it's most likely a review. But if you're watching this for the first time as a catch-up for class, you may need to come talk to me so I can explain a little bit better to you, okay? All right. But anyhow, when we're looking at these examples, each element is going to be giving off a very specific wavelengths of light, and we will give this and actually call it its fingerprint. So we can actually identify elements based on what kind of light they're giving off. What's really cool is when NASA and other space programs, they can actually tell you what elements are on different planets because they're picking up the radiation from those elements, and they're actually seeing these wavelengths. They're seeing a pattern, and they go, wait a second, hydrogen exists on this planet because I'm recognizing and I can detect these faint lines that are being produced from that planet. It's actually pretty cool, or the sun, all right, these spectral lines. So that's actually how scientists know what's out in space, because we can't go out there, it's too far away. All right, it took 40, 50 years for just a Voyager mission to just go to the outer rim of our solar system. The nearest star would take 1 million years just to go there and see it. It's too far away. But because we see the type of light that's being emitted from these places, we actually can make predictions about what's there. And based on these lines, we know that hydrogen exists there. We know that helium or sodium exists on these different planets or in these different stars. Pretty cool. All right. Now, this unknown sample is probably going to be strontium because it matches up with strontium. Okay. You're going to do this in the lab with a flame lab too. Okay. All right. So now we have the Bohr model. Okay, let's talk about what the Bohr model is. So actually, I'm going to show this image. The Bohr model is this. It's got the nucleus, and instead of having an energy cloud where electrons are just zipping around, they actually form and they follow in these rings. Okay, so electrons will actually stay in what we call energy levels. Energy levels are represented as rings. So this is the first energy level, this is the second energy level, and it goes all the way out. It can have up to many levels, 7 or 8 or more. Okay. Now, if we look here, I want you to write down this definition. So the fixed energy levels of an electron can have are called energy levels. All right. And when we think about how electrons interact with energy, it's more like walking upstairs than a ramp. Because in a ramp, there is an infinite amount of steps that you can take to get to the top. While in a stair step, there is a specific amount of space that you have to take a step to get up to this level, right? There's no intermediate level in between where she's stepping, all right? We have to take the full step to get to the next step. It's kind of like a slinky. If you had a slinky and you let it go down the stairs and it kind of bounced down, if it didn't have enough energy to get to the next step, would it go? No, it would kind of, and then it'd come back and settle. It would stay on this step. While if you put a slinky on this slope, it would just slide all the way down, right? Because there's infinite amount of steps, right? There's nothing stopping it from going down. So atoms act more like stair steps than they do as like a full spectrum, okay? So if we look here, we have an example of how light and energy interact with atoms. Okay, when I say light, I'm also referring to energy, okay? It can be infrared light. It could be gamma rays. It could be X-rays. Okay, these are all different types of radiation. Not radiation, I would say they're different types of wavelengths on the electromagnetic spectrum, and we classify it as energy. And the energy interacts with matter. If you remember back to my beginning videos, energy and matter, in this class, we're considering them to be separate things, and energy interacts with matter and causes it to change, okay? Now, if we look at this Bohr model, we have this energy level 1, this electron's on it, but can an electron exist in between the levels? No, it's like a stair step. It's got to jump to the next level. And energy levels get higher as you go out. It takes more energy for an electron to exist out here than it does down here. We call this the ground state. This electron is in the lowest possible energy level, okay? Now, light is a form of energy, okay? Visible light, okay, is going to interact with this electron, and it's going to cause this electron to gain energy. And if it gains enough energy, it will jump to the next energy level, right? And it'll absorb that energy. And if we look to this picture, we can see that this electron is now officially jumped. But here's the problem. This electron can't stay here. It's too excited. It's in an excited state, and it's unstable, and it's going to fall back down. And as it falls back down, it will release energy equal to the amount of energy that it absorbed, right? Law of conservation. So if we think about light is hitting this electron, it's going to gain just enough energy to jump to this level, It's going to be excited for a while, and then it will automatically fall back because it's unstable. It wants to stay in the ground state. That's where it's happy. And that light will be given off. And if you notice, this is red light, right? Now, what if I had something like purple light? Okay, purple light has much more energy than red light does. So if I imagine this, purple light hits this, it can make it jump to a third level, right? If you drew another ring around this, you could, and that electron could jump to the third level, all right? And then it could fall back down and it would release that purple light. Now, what would happen if I had something like green light, which is between red and purple, right? Because red light has the lowest energy, while purple violet light has the most energy, all right? Now, green light's in between that. So could we make our electron jump kind of in between levels? We can't. So this atom will only release red and purple light, essentially, because it can't release green because it can't fall in between. So if you look here at hydrogen, again, you don't see it releasing a lot of green light because when it jumps up an energy level, it doesn't have the energy equivalent to what green would be, while strontium does, right? Those electrons can jump to those levels, right? So these electrons can jump to equivalents of purple, kind of this bluish, teal, and these orange layers, right? And those are very specific wavelengths that hydrogen can absorb, okay? So the idea here is that energy is interacting with electrons, and they're moving energy levels. And we call this the Bohr model, okay? Bohr model. These electrons are bouncing between energy states. They cannot jump in between. And when they fall back down, they release energy equal to what they absorbed, right? That's the big idea. Right, so when we do a flame lab, you'll actually see different colors being produced, and what you're seeing is a culmination of all the different lights of energy levels of electrons being jumped up and down too. Okay, let's see this last page. All right, we can describe this just a little bit. Okay, the Bohr model is one way that we describe what an atom. Okay, and this. Basically, I've described this. So this inner layer is referred to as the inner layer, and it is the lowest energy level. So electrons will always want to fall to the lowest level. That's where they want to be. It's where their ground state is. Okay, and when they get excited, they jump up levels. I mentioned there was a picture somewhere in here I liked. Yeah, it's kind of like this guy here, this yoga guy, right? Is it easier for him to lay on the floor or suspend himself in the air? Probably to lay on the floor. He could probably do this for 30 seconds. I don't know. He seems pretty buff. Maybe a minute, 2 minutes. But eventually, what happens? He's got to fall back down to his ground state, right? So it's kind of like this. He's using energy to put himself up, and as he falls, it's like he's kind of releasing that energy out and around. That's kind of how atoms do it. But when atoms are in an excited state, they're kind of like this yoga guy. He cannot stay here. He's got to come back to the ground eventually. And that's how atoms are. If this electron jumped up a level, it's going to want to come back down, kind of like that yoga guy. And we can imagine different elements with different amounts of electrons as having filling up their energy levels. All right, so you can fit 2 electrons in the first energy shell, and then the next energy level, not shell, but energy level, you can fill in 8. So this first one we have to fill in the ground state, and then we can start to fill in the outer ring. And then once that's filled, we fill the next ring. So we have to work our way out. All right. And these ones that are out here, they're harder to hold on to, and it takes more energy. That's why they're considered a higher energy state. Okay? If you have any questions, please come talk to me. This is just a good overview of everything we've talked about in class. If you've got questions, please come talk to me. We are going to do a lab on this and go through this in more depth. Okay? Thanks again for watching. Until next time.